Welcome, everyone. For today's prep, we're going to introduce our last type of limit, and that is limits at infinity. So let's take a step back and think about all the different limits that we've seen so far in this course. And they've all centered around what happens to our function as the input value x approaches a specific number. So we've done things where limits where x, say, approaches 2. We've done right-hand limits. We've done left-hand limits. And we've kind of investigated what happens to our function as the input values get close to that specific number. Well, there's kind of two other places we can kind of investigate to see what happens to our function as we change our input. And those two other places, we sometimes call those the end behavior of our function. So we have the right end behavior. And we have the left end behavior. We might use this terminology from time to time. All right, so what would the right end behavior of our function look like? Where would we be kind of looking? Well, we're not going to be looking at a specific number here, a specific location on the graph. What we're going to be doing is we're going to watch what happens to our function as we move further and further to the right along the curve. So we're going to be moving in this direction. So we're going to see what happens to our function as we travel further and further to the right. And then we also have our left end behavior. So our left end behavior, but we're going to be going in the opposite direction. We're going to see what happens as we move further and further to the left. So we're going to let these input values get larger and larger negative, and we're going to see what happens to our function as we go further and further in that direction. So for our right end behavior, the notation we're going to use is the limit of f of x as x goes to infinity. So we're using x values that are going to be getting larger and larger positive. So we say x is going to go to infinity. So we're going in the positive direction there. And then for the left end behavior, we're going to, you can probably guess, we're going to use minus infinity. So we're going to investigate our function as the input x gets larger and larger negative. There you go. All right, so what are some of the things that can happen? Well, a few of the options is, and I have these written for x approaching infinity, but the same thing applies for x approaching minus infinity. So let's look at the kind of the first one here. What can happen is if we're calculating this right end behavior, so we're looking at our function f of x and we're watching what happens as the input values x get very large positive, what can happen is the output of our function can get very close to a number L. So this limit at infinity, where x is going to infinity, the function might just kind of settle down and approach a specific number. It might approach a number. Now it can also get very large positive. So the output value can get very large positive. So if our function values are getting bigger and bigger, we say that the limit would be infinity. And then kind of the third option is that if our output values are getting larger and larger negative, we would use minus infinity here. So when we're looking at all of these, again, it's helpful to kind of remember, especially for these ones where there's kind of different infinities there. When we look at each of these, this is describing the input of our function. So in each of these, the inputs x is going to infinity, gets large positive. And the result of our limit is describing the output of our function. So if the input x is going to infinity, there's a few different options. The output of our function f of x can just approach a specific number, or the output of our function f of x can also get really big positive, or it can get very large negative. So these are kind of the different options here, or it might just kind of bounce around and it doesn't kind of go in any one place. So we'll see examples of that. Okay, so we'll consider the numerical example in class. I just want to look at a couple graphs. And something special happens when our limit, either the left end limit or the right end limit, is equal to a number L. And when that happens, we have something on our graph that's called a horizontal asymptote. So if we have a function y equals f of x, and we calculate either the limit as x goes to minus infinity or the limit as x goes to infinity, and we find that either of those limits is equal to this number L, well then the equation y equals L is called a horizontal asymptote. So kind of graphically, what would this look like? So let's kind of see two examples here. So here we have, in the first graph here, we have this function, and it's kind of got a little oscillation to it. It's bouncing around. But we see that the height of those peaks kind of starts to settle down and starts to decay over time. And what happens is, as we could say the limit of f of x in this case, as x approaches infinity, is equal to 1. So as we move further in this direction along our x-axis, the height of our curve here is getting closer and closer to 1. So our function is kind of approaching that line. So in this case, y equals 1 is, we would call it as a horizontal asymptote. And probably just a lot of times abbreviate that HA. And just a little note here, when we specify horizontal asymptote, it's not, 1 is not the horizontal asymptote, it's y equals 1. So just a little, we need the y equals. As part of our line. Because what we're doing here is we're just specifying an equation of a line. So you got to have some variables for a line equation. And for a horizontal, it's in the form y equals. So, you know, when we're doing these, you're going to be tempted, we'll calculate the limit. We'll see that the limit's 1. So you'll just say 1 is the horizontal asymptote. Just be careful. It has to be y equals 1. Y equals 1 is the horizontal asymptote. Okay, so another graph, just to kind of see what's happening as we calculate these limits. So here we have a function, and if we look at the right end behavior, what's happening to our function? Well, we see that the height of our function, the output of our function, is getting closer and closer to that line y equals 2.5. So we would say, in this case, that the limit, the right end limit of this function as x approaches infinity is 2.5. Now, what about the other side? So we can also, in this graph, we have a little bit more information about the left side. This graph, we didn't really have that. And there was kind of some evidence that this would actually kind of be increasing in amplitude over there. So, you know, we don't really have enough indication of what's going on the other side here to say what the left end behavior is, but there's maybe some indication that maybe it doesn't exist because it just kind of keeps bouncing higher and higher. But in any case, this graph does have more information, and here we can say that the left end behavior as x approaches minus infinity. So as we move further and further to the left there, the height of our function is getting closer and closer to -1. The graph of our function is getting closer to that horizontal line. So the left end limit would be -1 in this case. And then this function has two horizontal asymptotes. So y equals 2.5, and then y equals -1. So those are our two, in this case, two horizontal asymptotes. Okay. So now graphically, if we're kind of looking at a function, and we see that if we look further and further to the right or further and further to the left, and we see that it kind of is approaching a line, well then we know that the limit is equal to the height of that line. Okay. So we're going to want a more algebraic way to calculate these limits at infinity. And the two most common limit properties here that we're going to be looking at are for power functions x raised to the power n and 1 over x raised to the power n. And then we have some other ones here which we'll talk about in class, but I want to kind of start with these two. So x to the power n, power function like this. Now, depending on if this exponent is even or odd, we kind of get two different behaviors. So if this is an even number, so like 2 or 4 or 6, all of those power functions have this kind of shape to them. And we see that as we move further and further to the right here, the height of our function is getting higher and higher. So we say that it's equal to infinity. And then for even power, if we go to the left, if we look at the left end behavior, well, it's getting higher and higher over there as well. So when n is even, if we go in the negative infinity direction, the output of our function goes to infinity. So again, it's kind of tricky. These infinities are talking about the output of our function. These infinities are talking about the input of our function. All right, so what about an odd power? Well, if it's an odd power, so like x cubed or x to the power 5 or x to the power 7, well, they all have this kind of look to them. And we see that if we look at the right end behavior, the height of our function is getting higher and higher. So same kind of thing applies. The limit of x to the n is infinity. Now, if we look at the left end behavior, so if we go in this direction, well, the height of our function is getting lower and lower. So it's going to minus infinity. Okay. The other case I want to look at is, for right now, is these functions 1 over x to the n. And again, you can kind of think of this even and odd powers. So if n is an even, so like x squared or x to the 4th, all of the even power functions like this have this kind of look to them. And you could see the right end behavior, the left end behavior, they're all approaching the x-axis. They're both approaching the x-axis. So the limit here is 0. So that actually tells us we have a horizontal asymptote at y equals 0. Now, if it's an odd power, so again, things like 1 over x cubed or 1 over x to the power 5 or even just 1 over x, they're all going to kind of have this look to them. And again, the graph looks a little different, but if we look at the right end behavior, again, the height of our function is shrinking down towards 0. It's shrinking towards the x-axis. So the right end behavior is 0. And if we look at the left end behavior, we're also getting close to the x-axis, but just kind of from the other side. So even in the left end behavior, it's still 0. So these are kind of nice. Really doesn't depend on the exponent if it's even or odd. These 1 over x to the n's, the limit in either direction is 0. Okay. And then also, limit of a constant is just the constant, so nothing too surprising there. And you can kind of see If we go to the right end, the constant function just stays flat, so it's kind of its own horizontal asymptote. And if we go in the left end direction, again, the constant function just stays flat, so it's its own horizontal asymptote. All right, so these 1 over x to the n's, though, these are kind of the algebraic key to kind of working with infinity. And like I said, we'll see some more examples in class, a whole catalog of functions here. But I want to look at one example, and that is this function 3x squared minus x minus 2 over 5x squared plus 4x plus 1. And we want to investigate this as x goes to infinity. So our strategy here, if x is getting really big, kind of the tricky thing here is that the numerator is going to get really big because we have a 3x squared. And then the denominator is also going to get really big because we have that 5x squared there. So there's kind of like a competition. The numerator wants to get really big, but when we divide by something that's getting really big, it kind of wants to make the whole fraction small. So there's this kind of competition. And the way we deal with this algebraically is this x to the power n method. So we're going to identify the largest power of x in the denominator, and then we're just going to divide every single piece in our function by it. We're going to kind of multiply both the numerator and the denominator by 1 over x to the n. So in our case, the largest power of x is this x squared in the denominator. So that's kind of step one. Pick out the largest power of x in the denominator. And once we've done that, then we're going to kind of, well, actually we can do this. We're going to multiply the numerator by 1 over x squared, and we're going to multiply the denominator by 1 over x squared. So all we're doing here is we're multiplying by a fancy 1. Now when we distribute this, we get 3x squared over x squared minus x over x squared minus 2 over x squared all over 5x squared over x squared plus 4x over x squared plus 1 over x squared. X going to infinity. So I'm just kind of distributing that. Distributing the 1x squared to everything over here, and then distributing same thing in the denominator. And when you get the hang of these, you can kind of just jump right to this step. And then we simplify this down. So the first fraction, the x squareds just cancel, and we're left with just a 3. The second fraction, we get a little bit of canceling with the x's. So we have 2 copies of x and then 1 copy of x in the numerator. So when that simplifies, we're left with just 1 copy of x in the denominator. And then that third fraction doesn't simplify anymore. All right. So then in the denominator, same kind of deal. The x squareds cancel, so we're left with just a 5. Then this x cancels with one of the x's, but we're still going to have 1x left in the denominator. So we're going to have 4 over x. And then we got our 1 over x squared, with x going to infinity here. And this is where we can kind of see the difference between what we started with. Each of these x terms, if x was going to infinity, each of these x terms is going to infinity. And infinity is not actually like a regular number where we can do regular arithmetic. So it doesn't make any sense, infinity minus infinity. But over here, or infinity divided by infinity, that doesn't make any sense as well. But over here, these fractions with all the x's in the denominator, these fractions, as x gets really big, these fractions all go to 0. So they're not going to infinity anymore. They're actually going to a specific number, and it's a number that we can do regular arithmetic with. So what do we end up with? Well, this fraction goes to 0, this fraction goes to 0, this one goes to 0, and this one goes to 0. So what we end up with is 3 minus 0 over 5 plus 0 plus 0. And that simplifies to just 3 over 5. So we're going to practice more of these in class, but the idea here is we're kind of taking terms that are all going to infinity, and we're kind of converting them into terms that are all going to 0 so that we can do regular arithmetic with. All right, so we'll see you in class. Bye-bye.